Hi, in this lecture, we will introduce some of the fundamental mathematical results that are needed for our series of lectures on an introduction to cryptography. So we will review only some of the math aspects that will be mentioned in subsequent videos and in subsequent modules. In particular, we'll start with recalling some important notions of probability, okay, and understanding what is probability theory and how this impacts cryptography. We'll also talk about statistics and show how a statistical analysis of a simple cipher can lead to a total break. Then we'll talk about number theory. So it's going to be very elementary number theory, so very elementary because we don't want to get too much into the details, but we will talk about reductions, modulo a certain number, and so the integer divisions that we have to perform in order to understand some of the most important public key crypto systems. And finally, we'll touch on something important from a computational standpoint, which is what does this mean for something to be hard? So we'll see in particular that nothing is really impossible for computers, just it needs to be very expensive in order to guarantee, to give certain security guarantees. So let's get started with probability theory. So what do we mean by probability? So for each possible event, we associate a number between 0 and 1. And if the probability p, which is that number, is close to 0, what it means is the event is very unlikely. On the other hand, an event that has a probability close to 1 is an event that is very likely to happen. Now, all the possible events, all the possible outcomes of an experiment, the probabilities have to add up to 1. Okay, that's the very sort of elementary property of probabilities. So how do we calculate a probability? So an experiment has a number of possible outcomes. Okay, so we'll give you the example in a minute of rolling a dice. Okay, so you have a bunch of different outcomes of an experiment and you count them all. And then your event corresponds to some of the outcomes. And then you can count also that number of outcomes that correspond to your event. And then the probability is just the quotient, the fraction between the number of outcomes corresponding to your event divided by all the possible outcomes. So quickly, let's see this in light of an example. So if you're rolling a dice, all the different outcomes are the numbers you can draw between 1 and 6. Okay, there are 6 different outcomes. Now, the probability of getting a 6, well, that event, so getting a 6 is an event. How many outcomes are associated with that event? Well, that's just the 1, which is I drew a 6. So the probability is 1 over 6. Now, if my event is I draw a 5 or a 6, so what are the outcomes associated to that event? Well, there's drawing a 5 and drawing a 6. So that's 2 different events. Sorry, 2 different outcomes for that event. And so the probability is 2 over 6. Now, a very important case is that of bit strings, because in computers, information is encoded as zeros and ones. So a bit string is a sequence of 0 and 1s. And the question is, so to calculate probabilities about drawing a certain bit string, it requires you to count all the possible bit strings. So the number of bit strings of length n is 2 to the n. Now, let's see why on an example. Let's say you're interested in bit strings of length 3. So here below are all the bit strings of size 3. So starting with 0, 0, 0, ending with 1, 1, 1. And you can see that we have 8 of them, which is 2 to the 3, where I've replaced n here by 3. Okay, so I know how to count the number of possible bit strings, and that will help identifying probabilities of drawing a particular bit string among all the possible bit strings. So let's say the secret. So there's in cryptography, there's always a secret, and you don't want an adversary to guess the secret. So you need to hide that secret, that it needs to be a bit string that it has enough length so that there are enough possible bit strings that are not the secret, right? So if it were, say, a bit string of size 3, well, with only 8 possible such bit strings, I would say the adversary has a chance 1 out of 8 of guessing a secret that you have that it's encoded over a bit string of length 3. So how long does a bit string need to be in order for a random guess to be too hard? So typically, we have, so the probability, of course, will be 1 over 2 to the n. That's 1 divided by all the possible bit strings. And what we consider to be sort of impossible is if n is, say, 80, but really more conservatively, let's say 128. So if n is 128, then a probability of guessing a bit string of length 128 is 1 divided by 2 to the 128. And this we consider to be something so unlikely that, in fact, it will never happen. Now, in cryptography, everything has to be with respect. I mean, all the security that we define has to be defined with respect to a probability of success of an adversary guessing the secret that is not 0, but very, very small. And very, very small is 1 over 2 to the 128. This we consider to be so small that we just simply disregard this possibility, okay? Now, another event for which we want to be able to calculate probabilities is that of finding collisions. And that will be more clear why we care about that when we discuss the case of hash functions more in details, in particular, what their role is in cryptography. However, to explain this from a math perspective, I need to give you some sort of idea of what a hash function does. So a hash function is simply a function that goes from a domain to a range, okay? Now, what it is to find a collision means you find 2 inputs in the domain that map to the same output in the range. That, if the x and the y are different, that is a collision. Now, for reasons that will become more clear when we discuss the role of hash functions in cryptography, we want that collisions be very hard to find. Now, they're never impossible to find, and that's for the reasons that we just mentioned before. We just want them to occur with a very small probability. So first off, if you're interested in the effort that you have to find to find a collision when there is a range of size n, then what's the kind of effort that you need to produce? Well, to be sure, so probably 1 means you're absolutely sure that you will find this collision, then you have to try every possible input, right? So you say x1 is my first input, I calculate the image, then I go with x2, I calculate the image, and I go with x3, and with x4 until I get x5, and then xn, okay? Then I have all the input, and I know now xn plus 1, whatever it is, it will have to map to something that has already been drawn, and that's because there's only n possible outputs for that function, okay? So now you know, at least when you get to the n plus 1th element in the domain, you're gonna loop back on some output that you've already calculated, okay? So you have yourself a collision. But n could be so large that, in fact, this is very hard to do, right? So if we keep n very large, then you know nobody's going to be able to find a collision with probability 1. Here's the problem, though. In cryptography, your adversary, enemies, people who are trying to break your system, they don't have to be successful with probability 1. In fact, they'll settle down for some reasonable probability of success. So it can get a little complicated to get the exact functions of finding the chances of getting a collision with respect to the probability. But let's say we're interested in 50% chance of success. Okay, So let's say you want 50% chance and you draw only, let's say you draw 2 elements in the domain. What's the probability of success? Well, you see you have the number of pairs here, x and y. These are your elements. And then the number of pairs xx, okay? This is what you want, the 2 images that are the same. And then these are the number of times, the number of elements that you have on the form xy, where x and y are arbitrary. So this gives you the probability that if you draw 2 elements and then your range has size n, you have 1 over n, okay? So, that's typically going to be small as n grows. But now, if you allow yourself to draw more elements, okay, you have a relationship. We're not going to explain too much how this is obtained, okay? This is outside of the scope of this lecture. But here's the situation. You have an inequality. If you want a probability of at least p, okay, let's say p is 50%, so 0.5, then you need the number k of elements you're trying, different elements in the range that you're trying, to be at least this value, which for a very large n is essentially square root n. So if k is at least square root n, or give or take, okay, these are like for large numbers, this is going to be essentially square root n, then you know that you have a probability p of finding a collision. So replace p by 0.5 to get your number k. That will get you a probability 50%, 50% chance of finding your collision. Now, there is an interesting instance of this problem, is what's called the birthday paradox. So it's a term that comes back a lot when people talk about the probabilities of finding collisions with the hash functions. So what does this come from? Well, you can say that you define the hash function that takes as input people and outputs birthdays, okay? Numbers between 1 and 365, okay? Each of those numbers corresponding to a day in the year. And then a very sort of traditional problem is how many people do I need in the classroom? So let's say, you have a classroom of students. How many students do I need in order to have a 50% chance that 2 students share the same birthday? Now, when I put it that way, the search for people who share the same birthday is essentially a search for a collision for that hash function I just defined, mapping people to their birthday. Well, usually the 50% chance prompts people to think that we're going to divide n, which is 365, by 2, and say, oh yeah, it should be about half, right? In fact, it's a square root of that number that you have to take. So only 23 students in the classroom guarantees you a 50% chance that 2 of those students will share the same birthday. And that's what people think about as a paradox, because, well, for most people, it's counterintuitive that so few students get you a chance of a collision, okay? Now, of course, you can easily convince yourself that this is in fact very reasonable, because we're not asking for those students to have their shared birthday on a particular date. Any date will do, and any pair of students will do, and that's a lot of possibilities, in fact. And that explains why you don't need that many students in the classroom. And that's something that has cryptographic implications, and we'll see that later, how, again, the search for collisions needs to be hard for hash functions to be cryptographically secure. But basically, it tells you how big the range needs to be in order for such a search to have a prohibitive cost. Okay, we just want it to be hard. And so if we want it to be hard, we have to set the number n so that even square root of n is a big number. So the search for people who have the same birthday, not really a hard task. But if n is giant, then you can hope that square root n is still a very large number. Okay? Now let's move on to a statistical analysis of a very simple cipher to show you how statistical properties of ciphers are very important for the security of a scheme. So a very traditional substitution cipher is the Caesar cipher. Okay, so we're gonna quickly review what the Caesar cipher is about. It was actually used by Caesar during the Roman Empire. And so the setup is this way. The key shared by the sender and the receiver is a secret shift of the alphabet. So basically a number between 0 and 25. If you say the shift is 3, what it means is the encryption is moving all the letters forward by 3. Of course, for moving Z, then you just loop. So moving 1 to A, 2 to B, and 3 to C. Okay, so what it means is you circle back to the beginning of the alphabet if shifting by 3 gets you out of it, of course. And then how do you decrypt? Simply by shifting backwards by that same secret number. Now, there's plenty of problems, of course, with that. Not the least of one is that there's only 26 possible keys. Okay, so that's really not that much. But there's something more fundamental about those kinds of substitution ciphers that is wrong, and it has to do with the statistics of certain messages to be encrypted. So this is just an example to show you what would happen with that shift of 3. So you can convince yourself very quickly that all these letters really are the shift of 3. Sorry, the shift of the original message by 3. And now what can statistics tell us about the ciphertext? Well, it has to do with the properties of the plain text, so the message that has to be encrypted. So it turns out in English, the most likely letter of the alphabet that occurs in a message is letter E. So in this particular message, I have 22 occurrences of the letter E. Now, what's happening with the ciphertext? Well, E is no longer, once we've shifted all the letters, E is no longer the most likely letter to occur. However, one of these letters is, and then in this case it's H, and because of the nature of the cipher, I know H has to be the encryption of E, okay? Under the assumption that I'm reading a text in English. But that means I learn the shift, okay, from E to H is a shift of 3. So that's it. I have learned the key just by looking at the ciphertext. It's really devastating. So this kind of statistical analysis and other statistical analyses are really important to see weaknesses in ciphers. Now, our last topic we want to discuss is number theory. So number theory, of course, is a very deep mathematical discipline, but we're going to just stay on the surface here by looking at some very elementary aspects of number theory that will occur in even the most basic definition, basic descriptions of what happened in public key cryptography. So we need to understand what it means to factor a number. So we have numbers that really can't be factored, and these are prime numbers. So prime numbers, well, they can always be divisible by something. 1 divides all the numbers, and all numbers are divisible by themselves, okay? And you can also do plus or minus 1. So a prime number is divisible by only plus or minus 1 and plus or minus itself, okay? And that's how we define them. So for example, 3 is a prime number because it's only divisible by 1 and 3 and minus 1 and minus 3. But 2 is not, okay? 2 can be, 4 is not, apologies, because it's divisible by 2, but also, and which is not 4, minus 4, 1, or minus 1, okay? So that's why 4 is not a prime number. Now, we have, and that's really important, that's going to, something that's going to come back in explanations about public key cryptosystems, is that once you have P and Q, so the operation of, so P and Q being prime numbers, the operation of producing the product of those two numbers is the multiplication. And going backwards, so given N, which is known to be a product of two primes P and Q, going backwards and finding the specific primes that occur in this decomposition is called the factorization. Now, factoring is considered to be a hard problem, okay? But what does that even mean? So you can always factor by trying every possible number that could divide your input, okay? And if you have enough time, you will succeed. So the question really is, could it be hard enough that no computer can succeed, okay? So here I want to draw for you two curves. One is the cost of multiplying two numbers with respect to the number of digits of these inputs, okay? So what we know is that we know very efficient multiplication algorithms. So ones that are almost linear in the number, the cost is almost linear in the number of digits of the input numbers, okay? So what it means is going from P and Q to the product of P and Q is quote unquote easy. Now, it's always going to be hard if those numbers are very, very, very large, but it's nowhere near the hardness of factoring, which is something, is a function that essentially behaves like an exponential in the number of digits. So here we have that going in a certain direction, so doing the multiplication, is something that we know how to do fairly efficiently, but going backwards is something that is actually hard, or at least that will take a long time, okay? Much more time than doing the other direction, multiplication. So this observation is really at the heart of asymmetric cryptography, where we leverage computational problems such as multiplication and its inverse, the factorization, where one direction is easy, the other direction is hard. Now, last thing that we want to discuss is modular arithmetic. So it's a fancy word just to talk about the integer division, the one that most of you guys know, and it means so from A to B, so A divided by B, you have a quotient Q and a remainder R, such that A can be written as Q times B plus R. That's it, right? That is the integer division of A by B. And so we say that this remainder, which is a value between 0 and B minus 1, it is called A mod B, okay? And this mod, so these modular values, are going to play an important role in public key cryptography, so much that I feel the need to mention that in this introductory video. So let's give you an example. What does it mean to have A mod 11? Okay, so here I'm fixing what's called the modulus. So here the B, so the number by which you're going to divide the input A. So what is it going to look like when I try A mod 11 for different values of A? Well, here you can visualize it with a wheel that has length 11. So if you take 0, for example, 0 mod 11 stays, it's still 0. 1 mod 11 is 1. 2 mod 11 is always 1. And that's, you can see because you can take the quotient to be 0 and set the remainder to be the same number, okay? R is A in this case. So for 0, 1, 2, and so on and so forth until 10, A mod 11 is still A. And then you move on to 11. So 11 mod 11 this time is going to collapse back to 0 mod 11. So it's going to collapse back to 0. And then you continue. 12 goes to 1, and 13 mod 11 is 2, 14 is 3, so and so on and so forth. And once you're done with your first, with this round, then you can move on to say 22, and then you're going to again collapse back to 0, and then 23 mod 11 is 1, and then 24 mod 11 is 2. Okay, so you can represent this as a wheel, and you just keep circling around and around. You can also do it backwards and go to the negative numbers. And you see that for each value, let's say 1, all the numbers that are equal to 1 mod 11, they're in fact spaced out by steps of 11. Okay, so you see it's 1 to 12, you got 11, and then 12 to 23, that's another 11 that you have to add, and 23 to 34, it's another 11 that you have to add. Okay, so that's how you can visualize. But of course, in the end, it boils down to just writing down the integer division of A by 11. Okay, so finding the quotient and looking at what's the remainder. So that's it for this little introduction to the mathematical notions that will come into play in other videos of this series on an introduction to cryptography. Thank you very much for your attention.